Have you ever wondered how gravity waves might affect our understanding of time travel? The concept might seem a bit outlandish, but it's an intriguing topic that's capturing the interest of scientists and laymen alike. Let's start by discussing the unseen nature of gravity waves. Picture a quiet, serene pond. Now imagine tossing a pebble into the center. The moment the pebble hits the water, it creates a series of ripples that radiate outward, disturbing the once calm surface. Gravity waves are quite similar to these ripples, though they are far more elusive. Just like the pebble's impact, massive objects in motion such as planets or stars can create distortions in the fabric of space and time. These distortions, or ripples, are what we refer to as gravity waves. They are the unseen silent waves that course through the cosmos, influencing everything in their path. However, unlike the visible ripples on a pond, gravity waves are invisible to the naked eye. They exist in the realm of the intangible, only detectable through the most sensitive of scientific instruments. Yet, despite their elusive nature, their influence is profound. They carry energy across the universe, bending the path of light and warping the course of stars. The concept of gravity waves is a cornerstone of Albert Einstein's theory of general relativity, which proposes that gravity is not a force, as Sir Isaac Newton suggested, but a curvature in spacetime caused by mass and energy. Einstein's theory paints a picture of our universe where space and time are interwoven into a single, dynamic fabric that is constantly being shaped and reshaped by the objects within it. So, just as ripples in a pond can alter the course of a leaf floating on the surface, gravity waves can change the path of objects in space. These unseen waves are the silent orchestrators of cosmic ballet, subtly influencing the movements of celestial bodies. As we delve deeper into understanding their nature, we open new doors to understanding the universe, and perhaps the possibility of time travel. But what creates these gravity waves that ripple through the fabric of space-time? Let's embark on a cosmic journey to the far reaches of the universe, where colossal entities like black holes and neutron stars reside. These aren't your ordinary celestial bodies. They possess immense mass packed into a relatively small space. When these massive objects accelerate or spiral towards each other, they stir up the cosmos, causing a phenomenon we call gravity waves. Picture this: two figure skaters, spinning rapidly in tandem on a frozen pond. As they pull their arms inward, they start to spin faster and faster. This is due to the conservation of angular momentum, a fundamental principle in physics. Now translate this image to a cosmic scale. Replace the skaters with a pair of neutron stars or black holes, spiraling inwards towards each other in the vast expanse of space. As they spiral inwards, their rotational speed increases just like our skaters. But these cosmic dancers don't just spin faster. Their immense mass and acceleration cause them to disturb the very fabric of space and time around them. They create ripples, just like a stone thrown into a pond. Except these ripples aren't in water, they are in the fabric of space-time itself. These are what we call gravity waves. The energy carried by these waves is immense. Imagine the energy it would take to shake the very framework of the universe. But despite their power, gravity waves are extraordinarily elusive. Their effects are so minute that for a long time they remained purely theoretical, a product of Einstein's revolutionary general theory of relativity. But don't be fooled by their elusive nature. Gravity waves are real, and their discovery has opened up a new way of observing the universe. They carry with them the secrets of the cosmos, waiting to be unraveled by the curious minds of humanity. Thus, these enormous cosmic dancers send out waves of gravitational energy, rippling across the universe. Gravity waves are elusive. How can we detect something we can't see? This question brings us to one of the most remarkable experiments in the history of physics, the Laser Interferometer Gravitational Wave Observatory, or LIGO for short. LIGO is a large-scale physics experiment and observatory to detect cosmic gravitational waves and develop gravitational wave observations as an astronomical tool. Imagine two massive L-shaped antennas, each 4 kilometers long, set up thousands of kilometers apart. Inside these antennas, a laser beam is split and sent down the arms of the L. When the light returns, it's recombined and analyzed. Now, when a gravitational wave passes by, it distorts space-time, and these antennas can pick that up as a tiny change in the length of the arms. It's a bit like feeling the vibration of music through a table. You can't see the music waves, but you can sense it. In the same way, LIGO doesn't see gravitational waves, it feels them. It senses the minute distortions in space-time caused by these waves. The engineering and precision involved in this are mind-boggling. The change LIGO detects is incredibly minute, about 1,000th the diameter of a proton. That's like trying to measure the distance to the nearest star to an accuracy smaller than the width of a human hair. Since its inception, LIGO has made several detections of gravitational waves, most of them from colliding black holes billions of light-years away. Each detection is a testament to human ingenuity and the relentless pursuit of understanding the universe. Through this incredible scientific achievement, we can feel the rhythm of the cosmos. The invisible becomes tangible, and the intangible, well, it becomes a part of our reality. And that is the beauty of science. It takes us beyond our senses, beyond the visible, and into the realm of the unseen, the unexplored, the mysterious. Through this incredible scientific achievement, we can feel the rhythm of the cosmos. Now let's shift gears to the fascinating concept of time travel, a favorite topic of science fiction writers. But is it really just fiction? Imagine time as a river, flowing steadily from the future into the past. Most of the time, the current is calm, moving us along at a predictable pace. This is what we perceive as the normal passage of time. But according to Einstein's theory of relativity, this river of time doesn't always flow in a straight line. Sometimes, it swirls around in eddies, creating what we might call a time loop. This is similar to the plot of many science fiction stories, where characters find themselves repeating the same events over and over again. But could this really happen? Well, Einstein's theory suggests it might be possible. You see, gravity affects not only space but also time. A massive object, like a planet or a star, can bend the fabric of space-time around it. This curvature creates what we feel as gravity, but it also means that time moves slower in strong gravitational fields. Now let's take it a step further. If something could create a whirlpool in our river of time, a strong enough twist in the fabric of space-time, it could theoretically trap time in a loop. This is the concept behind a time eddy. And then we have the waterfalls, where the river of time plunges over the edge. These are the theoretical wormholes, shortcuts through space-time that could potentially allow us to move backwards or forwards in time. Of course, all these ideas are purely theoretical. We have no practical evidence of time loops or wormholes. They exist in the realm of advanced mathematics and physics, far beyond our everyday experience, yet they remain intriguing possibilities. After all, many scientific truths were once considered fiction. The idea of atoms, the concept of an expanding universe, the existence of black holes, all were once speculative ideas that have since been confirmed. The manipulation of time, it seems, lies within the realm of possibility. So how do gravity waves tie into the concept of time travel? Well, let's dive in. To understand this, we first need to talk about wormholes. Now, wormholes aren't your everyday garden variety. They are theoretical passages through space-time that could create shortcuts for long journeys across the universe. Imagine you have a piece of paper representing the universe, and you want to travel from one end to the other. Normally, you'd have to traverse the entire length of the paper. But what if you could fold the paper in such a way that the two ends meet? And then, what if you could punch a hole through those ends, creating a direct path? That's the basic idea of a wormhole. Now, these are just theoretical constructs. We've yet to find concrete evidence of their existence. But if they do exist, they could be influenced by gravity waves. You see, gravity waves are distortions in the fabric of space-time caused by massive objects accelerating or decelerating. These distortions ripple outwards, much like the waves created when you throw a stone into a pond. So, if a gravity wave passes through a wormhole, it could, in theory, cause the wormhole to oscillate or wiggle. This oscillation might allow for the wormhole to remain open for longer periods, potentially long enough for something like, say, a spaceship to pass through. And here's the kicker. If you can travel through a wormhole, you're not just moving through space, but also through time. You see, space and time are interconnected, forming a four-dimensional fabric known as space-time. So a shortcut through space could very well be a shortcut through time as well. In this way, gravity waves might not just ripple through space, but also through time itself. What does this mean for our understanding of the universe and our place in it? Imagine standing at the threshold of a grand library, its infinite shelves laden with countless volumes of knowledge, each book a testament to the universe's mysteries. The discovery of gravity waves and the potential for time travel is akin to opening a new chapter in this cosmic book. It's like being given a key that could unlock a trove of untold stories about our universe, its origins, and its destiny. Let's contemplate the implications of this. Picture, if you will, the potential advancements in space exploration. Manipulating gravity waves could lead to faster-than-light travel, shrinking the vast distances between stars into manageable journeys. We could venture beyond our solar system, reaching distant galaxies and nebulae that have so far only been observed from afar. We could become true explorers of the cosmos, not merely observers. But it's not just about journeying to the stars, it's also about journeying back in time, back to the very birth of the universe. By understanding and harnessing the power of gravity waves, we may be able to glimpse the Big Bang's first moments, answering fundamental questions about how our universe came to be. It's like having a front-row seat to the greatest show in all of existence. Moreover, this could redefine our understanding of time itself. Is it a river, flowing in one direction, or is it a vast ocean, where past, present, and future coexist? Can we dip our toes into the waters of yesterday, or leap into the waves of tomorrow? These are the questions that the study of gravity waves and time travel might help us answer. So as we stand on the precipice of this new chapter, let's not forget the magnitude of what lies ahead. We're not merely rewriting the laws of physics, we're reshaping our understanding of reality. We're redefining our place in the cosmos, becoming not just inhabitants of the universe but active participants in its grand saga. The possibilities are as endless as the universe itself. Gravity waves and time travel, two complex concepts yet so intrinsically linked. We've journeyed through the unseen waves, unraveling the science behind them and their elusive detection. We've pondered whether they're simply science or verging on fiction. The relationship between gravity waves and time travel, as intricate as it may be, has potential to be the key that unlocks unexplored doors in our understanding of the universe. These cosmic ripples, these undulations in the fabric of space-time, are not just abstract scientific concepts. They are tangible, measurable phenomena that could, if we learn to harness them, give us unprecedented control over our temporal existence. As we stand on the precipice of this new age of discovery, we are reminded of the vastness of the unknown and the infinite possibilities it holds. As we continue to explore these cosmic ripples, who knows what we might discover? Perhaps in the not-too-distant future we might even find a way to surf them through time.